August 3rd, 2016. Guys, you're looking at LASCO C3 satellite images, and we're looking at the sun. You're going to see a sun-diving comet come in from the bottom right corner as it starts to get larger. You can see it now. As it gets closer to the sun, this comet and many that we have seen before expands, and right there, guys, you'll see that flare. It's an optical flare, but there's a 4-hour skip here. And then what you see in this camera is a CME, and after 12 more minutes of skip, after that 4-hour skip, we see a coronal mass ejection, leaving the exact opposite side of the comet collision. I've seen it many times in the past. You guys who watch the channel have seen it too. Now, same satellite, but this is a closer camera as far as the perspective that we see. Because it's so close, we will not see the comet strike the sun, because we're going to have that same 4-hour skip from 1600 to 2100 hours. See that? The comet's already struck the sun, and we're seeing the coronal mass ejection emerge from the other side. It's amazing to see this. Another question I had was these images coming from another satellite that gives us the same perspective as if we're looking at the sun from our planet. This is called the Solar Dynamics Observatory. And once or twice a year, you'll start seeing this ecliptical image. Now, that's played at real time, and we'll pause it. But what happens, guys, you've got to imagine a satellite that's trying to maintain an orbit close to Earth so that we can continue to get these Earth-facing images. I just want to note that that filament, guys, in the top right corner, let's pay attention to that. But what you're seeing here is the Earth, the actual shadow of our planet, because this satellite, the Solar Dynamics Observatory, orbits in a figure-8 fashion, straight up and down, not sideways between us and the sun, but straight up and down. And at certain times of the year, as that satellite dips down, it will come behind our planet. And all of this is to keep it in a perspective orbit so we get these images. So what is happening in these two is as the images are coming in, the SDO satellite is dipping behind our planet. It's not an eclipse from Nibiru or Planet X or anything like that. Now, moving to another satellite, but on the opposite side of the sun. This is stereo ahead. And that's why you see the comet come in from the opposite side. Here, the frames are not skipped, and we saw it come in. Guys, that was not one of the smaller comets we've seen. It's not one of the largest, but by far we've seen tiny comets come in. So that's why we saw that explosion. We will see some side effects of that coronal mass ejection expansion. It may be in the form of some 5.0 plus quakes. But guys, let's look at CERN a minute. They're running hot and heavy. Now, I just want to show you that they're at their 13 TeV collision point. And when they're talking about running this many collisions, they're talking about hitting degrees of, as far as friction and collision point temperature increases of 40 trillion degrees, and creating their own magnetic field. I'm going to go back to a video as we look at this. Notice that 2,076 bunches of protons hitting each chamber at 6.5 TeV, giving you 13. Guys, notice it's proton to proton, and it's almost going into alchemy when they're going to go into later in the fall, proton to lead collisions. But I want to pause here and show you a couple things. This is an older video that was done by CERN, but it explains very well what they're trying to do, and that's create a quark gluon plasma. And it's really taking time backwards into the time just before, I think, God locked the fallen angels away. And that's what they're trying to break free from. But check this out, guys. I got one other short video coming up about Hillary and Warren Buffett. So heads up, be safe.
In 2005, physicists at the Relativistic Heavy Ion Collider, RHIC, announced the discovery of a perfect liquid of quarks and gluons. Since then, scientists have been taking a closer look at this hot soup. One group has been looking back in time to the earliest point in the collisions to measure the temperature by looking at the color of light emitted. Think of looking at a glowing iron rod. As the temperature gets hotter, the glow moves from red to yellow and then white. At RIC, measurements beyond the visible spectrum reveal that the temperature reaches 4 trillion degrees, hot enough to free quarks and gluons from their individual protons and neutrons. Another group of scientists has been investigating a separation of charges observed at RIC. Because the colliding ions are themselves moving charges, they induce a magnetic field. This magnetic field and vortices formed within the quark-gluon matter lead positively charged quarks to move preferentially in one direction and negative ones in the other due to the existence of different symmetry properties within these vortices. This asymmetry at RIC may help scientists understand a similar violation of symmetry in the early universe that resulted in the predominance of matter over antimatter in our world.